Oh my goodness.
Okay.
Yeah, I'm so sorry. I forgot recording today's lecture up to this point. Let me just start doing in-class attendance. Oh my God. It's everything is routine. If I forget one thing, I forget everything. Sorry about that. In-class attendance. Yeah.
The first thing you remember is in-class attendance.
Yes. So welcome back, everybody. Oh my goodness. So yeah, I forgot to record today's lecture. So there are so many important pieces of information missing if you are not present today. So make sure, okay, make sure you understand who's not here, first of all, as a teammate. And that person needs to be well informed. You are the only person who knows about the first half of today's lecture. Sorry about that, because I forgot to record. So make sure you cover that information, share it with your teammates, especially Robert. I know Robert is not here. Who else is not here? Probably 4 people missing.
So the entire team.
Okay, so anyways, besides Robert, if you notice your teammate is missing, please cover the first half of today's class. I forgot to record it. I'm so sorry. Thank you, Matthew, to remind for reminding me. Okay, anyways, so let's just move on today. And I know it is recorded now. So let's move on with page 17 of Unit C2 example C25. This is a propeller-driven airplane example of range and endurance. Okay. All right. So this is Unit C2. Okay, let's move on. So range and endurance is different for propeller-driven airplane. So let's just go back and take a look. So this is a propeller-driven airplane equation of range and endurance. Of course, 2 different kinds of equation. One is the endurance average value method for propeller-driven airplane. Of course, the propeller efficiency, either prop comes in right here and right here. Then you're going to use the drag average value from beginning to end. And then this is the propeller-driven airplane brigade equation for endurance. Of course, you need information for initial weight and final weight and propeller efficiency. This is Bsfc, brake specific fuel consumption, Bsfc, not the TSFC. This is like essentially power, okay? And then, of course, CO3/2/CD. This must be maximum for endurance maximum. Somebody actually plotted using X55, right? Right, Jimmy? Your team. Who actually did it? I think David. David did it?
We all did.
You all did it? Yeah, of course. So you already have the brigade endurance equation in mind when you use X55, is that correct? Because that plot, maximum point means maximum endurance. That's what it is. Right? Okay, good.
All 3 of us.
Okay. Anyways, so that actually is a condition for this. 3CDO is equal to KCO squared. So this is a condition for maximum endurance. So you're going to pick up the brigade equation for endurance and the range. Range is basically endurance multiplied by velocity. Okay, so this is the endurance equation for brigade endurance for propeller-driven airplane. So let's just take a look at example C25 today. This is very, very weird problem. Surprisingly weird from Air Force Academy people think about this kind of problem, okay? Because this belongs to another Air Force Academy, this belongs to probably NASA. But anyways, let's just take a look. An aircraft is being designed to fly on Mars. Then you go like, what are you talking about? So airplane on Mars, okay, sure, it's 100% like a fantasy, but anyways, where the acceleration of gravity is 3.782 meter per second squared. This is the acceleration of gravity. So Mars's gravity is quite a bit lower than Earth's. Earth is 9.8. Mars is about less than half. Okay. Altitude, density is given. Density is 0.01 kilogram per cubic meter. Again, fairly thick, isn't it? Density is. The aircraft, no, it's not. Because our standard atmosphere at sea level is 1.125. So it's about, yeah, really thin air. Density is low. The aircraft will be powered by a piston engine driving a propeller. The engine has, when tested, burned 50 kilogram of fuel and 400 kilogram oxidizer because there's no oxygen on Mars, so you have to carry everything. So fuel plus oxidizer this is the total amount of fuel, of course. You have to add them together. So 1 hour, this is the 1 hour you burn 50 kilogram and 400 kilogram oxidizer together with it. Then producing 104 kilowatt of SHP, shaft horsepower. Okay. The propeller efficiency has been measured in Mars-like condition at 0.85, which is pretty high. I don't know if it's true, but the aircraft's drag polar is given. CD is 0.03 plus 0.07 CL squared. One important question for each team is, this is what you need out of X-5, you know, ultimately speaking. So X-5 using this software is determined this, okay? Drag polar. So this is the starting point of your performance computation. Anyways, and the wing area is 50 meters square. What will be the aircraft's maximum range and maximum endurance at this altitude on 500 kilogram of propellants? If its mass with propellant is 1,500 kilograms. So 500 kilogram propellants and overall mass. Oh gosh, how come not weight? But anyways, mass. This is kilogram mass. Okay. Anyways, so this is mass. So multiply by gravity to get weight. Be careful. It's not weight. It's mass. Okay. So what is the first step? Well, first step is I want to find out Bsfc. Let's determine Bsfc. Brake specific fuel consumption. Remember the equation Bsfc lowercase c is equal to fuel weight flow, W over dot F, divided by shaft horsepower. So fuel flow is fuel plus oxidizer added together 400 kilogram. You are going to expend it in 1 hour. So this is 450 kilogram per hour fuel plus oxidizer. This is just the mass. You have to multiply by the gravity, 3.72 meter per second square. This is the gravity of Mars, okay? Shaft horsepower you produce, 104 kilowatt. This is going to give you Bsfc, brake specific fuel consumption, lowercase c. You can get 16.1 newtons per kilowatt an hour, okay? So this is one information I need. This is especially required for both endurance and range. And okay. So first of all, let's find out the endurance. Endurance max. What is the condition? Anybody? Condition for endurance maximum. Condition for endurance maximum. This is the propeller airplane, different from turbojet type of fan. You should probably go back to this summary sheet. Here we go. So you're talking about propeller-driven airplane. What is the maximum endurance condition, which is this thing? Minimum power required point. 3 CDO is equal to KCL squared. Okay, so you're going to pick up this condition, propeller-driven airplane. Okay, minimum power required point. So the condition for that endurance max is 3 times CDO is equal to K times CL squared. So from this condition, you can determine what is the CL required for that. CL is equal to square root of 3 times CDO over K. So this is the 3 times CDO is 0.03. K is 0.07. Here we go. So this is 1.13. So this is the CL required for maximum endurance. So total drag CD is, of course, CD0 parasite plus K CL square induced. So let's just add them up. CD0 plus 3 times CD0, which is 4 times CD0, in which 4 times 0.03, which is 0.12. So this is the drag coefficient, this is the lift coefficient for the condition for maximum endurance. Okay. And next step, if we use 1500 kilogram, which is 1500 kilogram of what? 1500 kilogram of fuel, is that? Is this okay? And this is 500 kilogram of propellants. If its mass with propellants is 1500 kilogram, is this separately? 1,000 kilograms.
So that's total mass.
This is the total fuel mass, isn't it?
No, that's total aircraft mass.
Aircraft mass.
Fuel mass is 500 kilograms.
Yeah.
Ah, this is in, okay, so. Sorry, my original note is kind of confusing. So let's say 1500 kilogram multiplied by the gravity of mass, 3.72 meter per second square. This is going to give you 5,580 Newton. This is the initial weight. Yeah, this is initial weight. Final weight. Final weight is what? Final weight is, what's final weight? You use up all the propellants.
5,580 Newton.
80 Newton, that's right.
Yeah.
Thank you. This is the initial weight. And then 500 kilogram of propellants. Oh gosh. Another power loss, I'm sorry. I'm gonna complain like hell to that somewhere. This classroom actually, yeah, like randomly switch on and off. Okay, anyways.
They probably would.
Yeah, it's fine. So final weight, what's final weight? You use up 500 kilogram of propellant, so final weight is 1,000, isn't it? 1,000 kilogram is final weight multiplied by 3.72 meter per second square. This is going to give you 3,720, of course, Newton. This is a final weight, right? Final weight, use up all the propellants. Use all propellants, all fuel. Means fuel plus propellants, oxidizer. Fuel plus oxidizer, use all fuel. So this is initial and final weight, that's right. So from these information, you can now compute endurance, maximum endurance, which is, let's plug into endurance equation for brigade endurance equation. This is eta prop, propeller efficiency divided by Bsfc, multiplied by CL to the power of 3/2 over CD, square root, okay, 2 times rho and S, final weight to the power of 1/2 minus initial weight to the power of 1/2. So eta prop is 0.85, 16.1. This is Newton over kilowatt hour. This is a Bsfc with units. CL is 1.13 to the power of 3/2. CD is 0.12. Okay. Plug into the square root 2 times density of mass is pretty low, 0.01 kilogram per cubic meters. Wing area 50 meters square. Initial weight, no, final weight, so 3,720 Newton to the power, sorry, minus 1/2. Wrong equation. Be careful, minus 1/2, sorry about that. So this is negative 1/2 power minus initial weight 5,580 Newton to the power of minus 1/2. If you compute through it, you should get hour, which is 1.599 hour. This is the maximum endurance. So that means you cannot even stay 2 hours. 1.59 hour. That's the maximum endurance on Mars. It's kind of, I'm not sure if I'm convinced, but yeah, it's reasonable. So next is maximum range, of course. Maximum range, what's the condition? Anybody? Anybody in classroom? Only 2 people. What's maximum condition of maximum range? We're going to go back to this summary.
CD naught is equal to KC.
That's right. So this is minimum thrust point, minimum drag point, to say the least. Okay, minimum drag, minimum thrust required, which is induced drag coefficient is equal to parasite drag coefficient. CD0 is equal to KCL squared. Okay, so this is the maximum range. Requirement is D min, minimum drag, which is usually maximum L over D ratio, right? And then here the condition is parasite drag is equal to induced drag coefficient. So from here, okay, maximum L over D is essentially same as CL over CD to the maximum. With the condition given here, we know that this is inverse of 2 times square root K times CDO. This is 1 over 2 times square root 0.07 times CDO, 0.03, which is 10.9. So this is the maximum lift to drag ratio. Okay. Obviously, as you design your airplane, X55 actually gives you this value. It actually plots lift to drag ratio over the range of alpha, right? So maximum range, you are going to plug in once again to the Brigade range equation, which is eta prop, propeller efficiency divided by Bsfc times CL over CD to the max. Natural log initial weight W1 to the final weight W2, the ratio of it. So this is going to be, once again, 0.85 over 16.1 Newton kilowatt hour. 10.9, this is L over D max, natural log. Initial weight 5,580 Newton divided by final weight 3,720 Newton. If you plug in those things, you are going to get the value of meters, and then you're going to convert it to kilometer, 841 kilometer. This is the maximum range. Okay. All right. Any question here? Now, obviously, the equation is essentially plug and chug. You really need to understand the condition to make it maximum. That is confusing. So this is the condition to make it maximum range. This is the condition to make it maximum endurance. This is condition to make it maximum endurance. This is a condition to make it maximum range. Let's be careful about that. Okay. All right, so we are going to wrap up range and endurance, which is quite an important subject, Unit C2. Next page. So next page is the range and endurance. There are a few quite important problems. One is, this is the maximum range. Okay. Endurance is a different subject, but the range, let's just focus on the range. Range is essentially endurance multiplied by airspeed. This is range. Okay? So for the same amount of endurance, if you fly faster, you are going to actually maximize the range. Does it make sense? So the range is a function of actually how fast you can actually fly, while you minimize the consumption of fuel. So let me repeat. Range is combined property. In other words, you have a certain endurance. Endurance depends on your fuel consumption, of course. So this is kind of hard to control. Once you design and pick up your choice of power plant, endurance is somehow very difficult to control. You cannot maximize endurance just as easy. In other words, endurance is somehow fixed based on your choice of propulsion system and also design of airplane. But range you can improve by how you fly it. In other words, range is endurance multiplied by velocity. Velocity, if the velocity is faster, you can maximize the endurance. Now that's something we can call, hey, let's fly higher altitude to maximize the range. We can do that. Okay? So let's think about flying higher altitude. Let's just zoom into this part. So this is same airplane, comparison between sea level and the 25,000 feet altitude. So if you are sea level, this is the thrust required, or basically drag. This is the thrust available at the sea level. Okay? So in order to have a maximum range, you're going to fly a line started from the origin, drawing line to the tangent, just touching this thrust required. This is the speed for maximum range at the sea level. It's about, I don't know, what's like 155, 160 knots. Okay? Now, if you change your altitude to 25,000 feet, 25,000 feet, of course, the drag will be changed here. This is the drag at 25,000 feet. This is the thrust available, 25,000 feet. Now, obviously, you can fly faster. This is the condition for maximum range. You can fly faster, which is 230-ish knots. So at the higher altitude, you can fly faster to maximize for your range. Because in this case, at the sea level, you can only fly 160-ish. At the 25,000 feet, you can fly 220, I don't know. How much percent increase of range you can expect? Wow, quite a bit. Not quite as double, but I don't know, 170% increase of range because you fly faster, okay? This is actually a propeller-driven airplane. So this is a piston-powered propeller-driven airplane. So this is a power plot. Obviously, maximum range is the same thing. You know, you're going to draw a line from origin, touching to the curve here. So at the sea level, you're flying, I don't know, 60 knots. At the 10,000 feet, you're flying faster, about 75 knots, I don't know. So you still have an increase, I don't know, 20% of range by flying 10,000 feet for this case. So let's just summarize what I'm talking about here. So by changing your altitude, you're going to change your range. So typically, if you can fly as high as possible altitude, you can actually maximize your range. But however, there's a limit for it. Limit is if you increase your flight altitude, you are going to actually fly closer to critical Mach number for high altitude. As a subsonic airplane, you shouldn't fly at critical Mach number because critical Mach number is quite frankly the maximum you can get without having any compressibility effects kicks in. Compressibility effects includes skyrocket exponential increase of your drag coefficient. Okay, if you go beyond the critical Mach number, you can actually introduce all of those difficulties for compressibility effects. So if you can fly critical Mach number at as high altitude as possible, that is something called the best cruise altitude. Okay, so that is the altitude. It is going to optimize your range. And the best cruise Mach number is the critical Mach number at that given best cruise altitude. Making sense? So how can you make your airplane maximum range? You are going to fly as high as altitude while you are not hitting critical Mach number. That is the optimum range, absolute maximum range. So let's take a look at figure 531. Maximum range cruise airspeed is 45,000 feet. This is 45,000 feet is the best cruise altitude. And then best cruise Mach number is the critical Mach number at this 45,000 feet altitude. So this is the plot here. Okay. So this is a plot for best cruise altitude and also best cruise Mach number. So this is an airplane at the sea level. This is the thrust required or drag. And this is a thrust available with afterburner. This is a thrust available dry. That means no afterburner. This is military power. Oftentimes, this is military power. No afterburner. Okay. Anyways, you are going to draw a line once again, starting from origin, straight line, just barely touching this drag. So at the sea level, this is airspeed for maximum range at the sea level. The value is a little bit shy, less than 300 knots, 290 knots, something like that. 290 knots, let's say. Okay, so this is sea level, but at the 45,000 feet, this is changed. This is a 45,000 feet drag or thrust required. This is the thrust available with afterburner with 45,000 feet. So this is the thrust available without afterburner, 45,000 feet. You're going to once again draw a line, straight line, touching right here. This is, here we go. This is the airspeed for maximum range at 45,000 feet. What's the value? 550? I don't know. 550 knots. Ooh. What do you mean by that? By flying 45,000 feet, the range is, whoa, about double. Isn't that right? Okay, so that's what I'm saying. Okay, so in figure 531, maximum range cruise airspeed at 45,000 feet is about twice the maximum range cruise airspeed at sea level, 290 versus 550 knots. Because Bsfc is actually lower at 45,000 feet, this actually also even stretches the endurance at the higher altitude. So endurance is higher, you're flying higher speed. That means aircraft range is more than doubled by flying 45,000 feet for this case. Okay. So this is the airplane absolute maximum range. Let me just write it down. Absolute max range. All right, here we go. So this actually concludes the discussion of Unit C2. Do you have any question? Unit C2 is a quite important unit, range and endurance. This was a huge stumbling block when I was undergraduate student. This is the reason why I quit being airplane performing aircraft design guy. I'm an aero guy. I don't have to deal with any of those kind of. So anyways, this is an important unit, guaranteed to show up for your exam 2. Guaranteed, let me repeat, guaranteed to show up as your exam 2 subject. Okay? Do you have any question, people online? Okay, so now we are going to get into Unit C3, okay? Unit C3. Unit C3 is just the performance constraints, sort of constraints, not the performance, but takeoff, landing, turns, level turn and vertical turn. Takeoff and landing, of course, requires both consideration of how well you designed your airplane, aerodynamically speaking, plus what is your capability of your power plant. So those two combined is going to constrain takeoff and landing. Takeoff means how short you can take off, well actually how short or how long you need for takeoff distance, okay? So this is essentially takeoff distance for conventional takeoff and landing type of things, okay? This is actually very, very simple deal. Let's just take a look at page 2, takeoff, okay? So this is a takeoff, sequence, just a schematic of it. Starting from 0 velocity, you're going to accelerate to the certain point, something called transition region. You're going to start rotating, come up with your takeoff attitude. You're going to pitch up, you're going to rotate your airplane, and then transition to the climbing stage. And then you're going to pass certain height, climb over obstacle. That is going to complete STO and then climb. STO is the takeoff distance starting from 0 all the way to the half of the transition point, STO, okay? This is a very simple equation of motion. This is the airplane lift and weight, thrust and then drag, and then this is the rolling resistance while your airplane is still touching the ground, okay? And this is normal reaction force for each wheel, okay? All right, so equation is based on the discussion. One of the most important discussion is we're going to choose airspeed 1.2 times the aircraft's stall airspeed. This is the takeoff speed. So BTO, takeoff speed, is 1.2 times airplane stall speed. This is quite an important assumption right here. Okay. Now, aircraft landing is essentially the exact same equation, just the direction opposite. You're going to slow down and touch down safely. So just a little bit ahead, but landing airspeed is actually 1.3 times V stall. This is the only difference, by the way, in the equation. Okay, we are going to see the landing constraints. Now, when we do an analysis for landing airspeed is 1.3 times V stall. This is actually approach airspeed, I think. Let me just double check. Landing airspeed, VL. Yeah, 1.3 times V stall, yes. I was not sure. Okay, let's just go back. So we want to find out takeoff distance. So takeoff distance can be found by equation motion for this figure in the direction parallel and direction perpendicular. So you come up with two equations, okay? Summation of the force in perpendicular direction is F equal to ma, okay? So mass times this is acceleration, centripetal acceleration, of course. This is F equal to ma, this is the tangential acceleration, A, okay? So those two. Now you're going to consider the loading friction coefficient because your airplane is touching on the ground. So friction coefficient depends on the condition of the surface. So 0.02 to 0.04 for paved runways, 0.08 to 0.1 for turf. And then of course in rainy day on concrete, you have a different value. So loading friction coefficient comes into play here, okay? So we are going to combine those two equations. You just plug in n equal to w minus l plugged into right here. You get this equation. This is the acceleration during takeoff. Takeoff acceleration. Okay, so takeoff acceleration is a function of course, gravitational acceleration. This is thrust and drag. This is loading friction coefficient. This is weight of takeoff weight. Okay. Now we are going to assume that this acceleration is constant throughout acceleration process. If the acceleration is constant, you can determine the velocity at any location during the process by integration from 0 to t1 dv dt dt. If the acceleration is constant, this comes up, okay? Velocity v1 is a times t1 anyways. So out of this assumption, you're going to move on. Then you determine time to take off. Time to take off is velocity divided by acceleration. Acceleration is constant once again. And then BTO, this is the takeoff velocity. We assume the 1.2 times B stall, right? So you just basically plug in this BTO right here, and then acceleration from previous page. Acceleration is previous page. This equation is going to be plugged in here. So this is acceleration right here. This is BTO right here. It's just plug in to find out time to take off. So this is the time to take off. Now, distance to take off, you're going to, once again, accelerate 1/2 ATTO squared. So this is time to take off square multiplied by acceleration 1/2. Okay? So everything's plugged in here. Right? This is 1/2 acceleration times time to take off squared. Then you're going to simplify. You come up with this equation. This is the distance to take off STO. Takeoff distance. Now, when you come up with takeoff distance, the important thing is the values within this bracket is going to change. At the very beginning, your velocity is 0. At the very end, your maximum velocity. Throughout the acceleration process, thrust and drag and loading resistance, everything changes. So we are going to take this value within the bracket at the condition of 0.7 times velocity takeoff. So this is the value within the bracket is taken as average at condition of 0.7 velocity takeoff. This is quite important. Drag changes, thrust changes, loading resistance changes throughout the acceleration process. We are going to take the average value, which is the value taken at the 0.7 BTO. Okay, so when you reaches to the 70% of the final speed of takeoff, how much thrust do you have? How much drag do you have? How much loading resistance do you have? We are going to take that value and then plug it into this bracket. Okay, that's what it is. Now, there are certain special cases. Special case is, suppose if your airplane comes up with oversized propulsion system, engine so strong, engine thrust is almost the same as your takeoff weight, which is big enough engine. If so, you can actually simplify it. This is a simplified takeoff distance because engine thrust is so large, you don't have to worry about any of those drag and loading resistance, blah, blah, blah. You just ignore it. Thrust is so big compared against those others. So you just pick up on this thrust, drag it in here. So this is simplified. Large engine, high thrust aircraft. High thrust aircraft. Then what is the requirement for high thrust? Takeoff thrust is about equal to the takeoff weight. This is big enough engine. And then you don't have to worry about drag and rolling resistance for the takeoff sequence. Now, today's jet airliners almost always just like that. The engine's so big, so you don't have to worry about rolling resistance or drag again. Okay, so just about 5 more minutes. So next class, we are going to take a look at example C31. This is a takeoff example. And then we are going to look at the landing constraints. This is also another performance. And then level turn and vertical turn. Okay, so that's the unit C3. Let's stop here today. Do you have any question? Yeah, go ahead.
Why do we choose 70%
That usually represents the average amount of changing thrust and drag and rolling resistance, because it is going to increase, right? And then you cannot, of course, you cannot choose the maximum value. You cannot choose the 0 at the very beginning. Yeah. So 70% represent like average value. Okay. Any other question?
Dr. H,
Yeah, go ahead.
would it be possible for you to post those what is it? What you showed earlier of what we should do for project 2?
I think this, right?
Yes. Would you be able to post that?
Yeah, I'll do. Yeah.
All right. Thank you.
Sorry about not recording the session at the first time. Any other question? Have a good day. Today's a Tuesday, so we're going to see you back on Thursday. We have no, yeah, we have.
Oh, we have
What's going on? This.
I think one of the bulbs might be bad.
Yeah. Then everything shuts down.
Probably.
Okay.
See, I would have laughed at his.
Yeah, I'm going to complain anyway.
I would have laughed on that one. Wait, Dr. H, can I check some homework with you real quick?
Yeah. Let me stop recording.